Hi. All right, now that we've reviewed our rules for differentiation for single variable functions, now we're going to move on to multiple variables. For example, your marginal analysis problems, your company has always just had one product. What if we wanted to maximize profit or minimize cost for a company that has two products? Maybe two types of shirts, a button-up shirt and a t-shirt, something like that. And then we can generalize this to n products. We let a computer handle the majority of the legwork there. But this will give you a taste of how we deal with calculus, or for that matter, just functions with multiple variables. The big difficulty, and the reason you've not done much in 3 dimensions, is that we can't draw in 3 dimensions. We can do mathematics there. We can do mathematics in 27 dimensions. We can't draw it either. So anything you've seen that has the appearance of 3 dimensions is just that. Any indication of depth is really a trick. It's kind of like you've all seen a sphere drawn, and usually someone does something like this, which gives the illusion that it's 3-dimensional. But this is still a 2-dimensional piece of paper or screen. And so it's what we would call an embedding of 3 dimensions into 2 dimensions. So we're not going to be drawing too many things by hand here, just because it is really that difficult. But we will do mathematics there, and we will do calculus there. So just a quick rundown of how we think of 3 dimensions. This down here, here's the x-axis, here's the y-axis. This is your xy plane. So imagine the xy plane being your desktop. And then to get a point in 3 dimensions, we go to a point in 2 dimensions. So there's a point on your desktop. And then we project up above your desk or down below your desk to get a point in 3 dimensions. It's the easiest way to visualize it. We live in 3 dimensions, and for some reason it's still tough when you actually think about it. We don't, on a day-to-day basis, think about the fact that we live in 3 dimensions. I don't. So the idea is you have a point in the plane that is being projected up to a height of c, or down. It could be down below. Okay, so if you look at the 3 pictures here, now we've got different planes. We've got the xy plane, the xz plane, and the yz plane. It's even hard on 2 dimensions to make a plane look correct, but you can kind of see what's going on. So the idea is just think of the xy plane as your desktop, and then a point, so this would be a point xy, and then say we project down to some point below your desktop, and that would be called xyz. That's really it. So even to get the representation of this point here in 3 dimensions, you have to draw this rectangular box here to make it look, like there's depth. That's just one point. Imagine infinitely many points on a surface. It'd be very difficult. Okay. There is a distance formula between 2 points in 3 dimensions. This part of it should look familiar. That's your distance formula, the square root of the sum of the squares of the distances between x and y coordinates. That's your distance formula for 2 points in the plane. It does extend to 3 dimensions in the same way. I just threw that in there. We're not really going to use this. But that's basically your introduction to 3-dimensional rectangular coordinate system or Cartesian coordinate system. Most of the pictures we're going to look at computer generated pictures, just because we're not going to be able to draw these things by hand. But we can do mathematics there. We do continue to use function notation, which is good. So nothing will be new there. It will really be, everything in this chapter is pretty much analogous to what you've seen in prior algebra and your previous calculus classes. Function notation works the way you think it would. The difference now is you have two independent variables, x and y, that are being plugged into a function to output some z value, or f of x, y. So it really is very similar to what you've seen in the past. There's just more independent variables. So two independent variables, and then the output, the range values, are your dependent values. Domain and range, they mean the same thing as before. Domain are the values you're allowed to plug into a function. So when we're talking about domain, we have three main issues. One, we can't divide by 0. Two, we can't take the square root of a negative number, at least in the real number system. And 3, we can't take the log of anything less than or equal to 0. So those are the things we look out for. Just want to go through a couple here where we just plug numbers or plug points into a multivariable function just to get used to it. The only trick here, and it's not a trick, the only thing you have to be careful of is that you do have two values x, y, and these are ordered pairs, so you have to make sure you plug things in the right place. Beyond that, it's pretty much what you think you would do. So f of negative 4, 6 would be 3 times the x value. So we're just plugging the x values where they go, the y values where they go. So 3 times negative 4 plus 2 times 6 over 2 times the x value, negative 4, plus 3 times the y value, 6. And then it's just arithmetic from there. The numerator, we have negative 12 plus 12. The denominator is not 0, so we do get 0 for a result. So we would say that the point negative 4, 6 is in the domain because we got a real number output. So 0 is a range value. Now, what if I want to identify the entire domain? These are problems you probably remember bothering you at the beginning of your Math 130 class or before in your algebra classes. It goes back to what I just said a second ago, is what can't we do is usually the way to go. There are no logarithms in this function. There are no square roots. There is a fraction. So what we need here is the denominator to not be 0. So we need 2x plus 3y to not be 0. So the domain will be all of the ordered pairs x, y, such that this is not 0. What we can do is we can solve for y here. So we want all the points not on the line that I'm going to obtain here, which will be negative 2/3 x, if I bring the 2x over and divide by 3. So the domain is all ordered pairs. So everything looks just like what you've seen in previous courses. There's just an extra variable. So all ordered pairs x, y, not on the line y equals negative 2/3 x. Not on that line. Okay. So think of your domain as the entire xy plane. Usually in 2 dimensions, you think your domain as the x-axis, and then you leave off what you're not allowed to plug in. Here, our domain is going to be the entire xy plane with a dotted line right here. those are values where you won't see any points projected up or down. Okay, hopefully that makes a little bit of sense. Let's look at the last one here on this page. So here we have square roots, so there could be an issue. Let's first just plug a value or a point in. So g of 2 negative 3 would be the square root of 16 minus 2 squared, that's your x value, plus negative 3 squared. Be careful with parentheses. We're squaring the negative as well. So we get the square root of 16 minus, this will be 4 plus 9, which is 13. So we get square root of 3. That's really it. So you're plugging in a couple values and you get a single output. And the idea of a function is the same as it was before. To be a function, for each ordered pair you plug in, you get exactly one output. Okay. Not multiple outputs. So what about domain? In this case, we need 16 minus x squared plus y squared to be greater than or equal to 0, or else we can't take the square root. So I can rewrite this as moving the variable terms over. And you may recognize this as a circle of radius 4 If I say circle of radius 4, that's what it is, regardless of how it turned out. So this says x squared plus y squared is less than or equal to 16. That would be everything inside. So in your xy plane, this is the domain. So points from here will be projected up or down to that surface. Actually, it'll be projected up. And in fact, the surface given by this function is actually a half of a sphere. So it actually, again, here's me faking things. It actually looks like that. And there's your domain. It's this circle, including the boundary because it's the or equal to. So your domain is all ordered pairs xy inside and on the circle x squared plus y squared equals 16. So that's a circle of radius 4. Since it's less than or equal to for the x squared, y squared, that's also including all the points inside. So we're taking every point inside here and projecting up to get this surface, which will be the upper half of a sphere. Okay, just throwing that out there. It's not totally important that you're able to draw these things. Don't be embarrassed by my wonderful artistic skills. The important thing is that you understand how to evaluate a function, and then the idea of what you can and can't do with a function based on domain. So those are not new things. We can't take the square root of a negative number in the reals, and we can't divide by 0 in the real number system. If logarithms were present, that's also something we'd have to be aware of. So if this was the log of 16 minus x squared plus y squared, or natural log, then the difference would be the domain would be everything. We would need this to be strictly bigger than 0. The domain would be everything just inside. So the difference would be your circle would be dotted, and your domain would be everything inside. And I have no idea what the surface would look like. Okay, so I wouldn't worry about that. Okay, so let's look at an application on the next page, page 3.